Hello, class. We're actually moving back to chapter 4 now. I don't know if you remember or if I mentioned this before, but we sort of skipped part of chapter 4 to move into chapter 5. Now we're going back. That's just kind of the way I like to do it. I like to start with the fundamentals of trig, then get into the triangle, then a lot of the applications, and then kind of work our way back to the often a little bit more tedious or less enjoyed sections on trigonometric identities. Now, these sections are actually really important going into calculus and understanding the way in which we work on trigonometry algebraically is quite important. So it's definitely something that is different, and a lot of people have a little bit of trouble with these sections, which is why I don't want to skip over anything or and whatever. But actually, before I get too much into identities, I did want to mention this, um, and that's that. We're following the schedule roughly, but I'm sending out an announcement about this too. But I've decided that we're not going to have a fifth exam, and that will just be part of the final. So we just had an exam not too long ago, and I feel like we don't need another one right before the final. Like it just seems like with the online environment, this doesn't really make much sense to me. So basically, this exam is gone. Well, it will be part of the final, and we'll talk more about what that means. But basically, the final will be a little bit more heavy on the chapter 5, and yeah, so hopefully this makes your life a little bit less miserable. You only have to worry about one test. The final is still cumulative, but and we'll still cover everything else to review. But anyways, yes, that I just wanted to mention that. But this week we're going to be wrapping up chapter 4. We're actually going to save this section on trig equations for next week. So next week we're going to work on trig equations, which is this whole another can of worms, and do a little bit of calculus prep. We probably will not have time to work on chapter 10, which is a little bit of a shame, but I'm sure you've seen a lot of that math before. But it might be a good idea that you just read through chapter 10, look it over, because basically in calculus, specifically in Calc 2, there's a lot of the algebra and the strategy behind trigonometry, sequences and series, etc., is going to be very fundamental. And my goal, kind of in these last couple weeks, is to make sure that you are ready to go for when you get into the sections that it will make a little bit more sense. Because I've taught Calc 1 and Calc 2 a lot, and one of the areas where my students really tend to struggle is with the more basic elements of trigonometry, like identities, the section we're going to get into right now, or sequences and series, more of the basics rather than the actual calculus concept. Also, in the last little section on calculus prep, I wanted to talk a little bit about limits. And kind of compare to a lot of the stuff we were talking about earlier in the semester, because when you get into calculus, things can seem very, very different, but it's just kind of alternative ways of thinking about and defining a lot of the ideas. Like end behavior, really, it's synonymous to what we refer to as the limit as n approaches infinity. But basically, I wanted to talk a little bit about what is a difference quotient, what is a derivative, just to kind of get you into the basics of that, and just so you have a little bit of a head start on Calc 1 for those of you who need to take it either in summer or next semester. Anyways, let's get back into trigonometric identities. Sorry, I got on a huge tangent there. Again, no pun intended. Very easy to do that in trigonometry. But basically, to start off with, what is a trigonometric identity? Well, the term identity is not a mathematical word that everyone may know, so I want to just mention what does that mean. But an identity in math is just what we refer to as an equality relation. It's something that is a true statement. So it's basically an equation, and the implication is that it's true. So there's many identities that I know you already know. Like for example, x plus x um, is not x squared, right? Oops, I'm writing this in a position where you can't see it thanks to my big fat face. X plus x is equal to 2x, right? That's something that, we often, when we're taking algebra class, our teacher tells us to memorize or whatever. But this kind of makes sense because if I take a number and add the same number to it, what I get is twice that value, right? 4 plus 4 is 8. That's just a basic principle. And what I'm saying there is that's the idea of what an identity means. It's something which is a mathematical statement. It might not be obviously true to everyone, but if you really think about it, it has to be true. That's what an identity is, and it's like a principle. It's a property or a rule that we could memorize. In trigonometry, there are a lot of identities, and that's the can of worms we're going to be opening in these next few videos. But basically, or another example of an identity would be, well, if I took x and multiplied by x, sorry, I can't write with my mouse very well, that would be x squared, because by definition, what an exponent means is the same thing multiplied, the base multiplied by the number of the exponent. So um, if I'm taking x squared, obviously the exponent's 2, that means x times x, and it's just true because of what the exponent notation is. But anyways, these are algebraic identities, and all sorts of properties that you've learned in algebra you could call identities. Um, but in trigonometry, there are so many different identities, and the way we use them is contextual. So where we're going to begin is talking about what we refer to as the fundamental trigonometric identities, or sometimes we call them established. They're ones that we've already talked about before. And then we're going to build from these and learn new ones, new rules, and kind of talk about, well, why are these useful? And a lot of the identities, kind of like in our last video, we were talking about the different formulas for how to find the area. Sometimes these formulas are not really that useful. It just really depends. Sometimes they are useful, and really, I think what is important is that you're aware that these identities exist and kind of understand the purpose of them and how we can use them and when they're going to be useful. Say, for example, in Calc 2, and I'll just try to give you my best tips on which ones kind of come back up later and might be good to remember. And for some reason, there's a bunch of memes in these slides, so you can just ignore those if you want. But starting with some of these established identities, all of these we talked about back in the first section of our trigonometric studies in sections 1 through 4. But basically, the reciprocal identities are all identities that are true because of the definitions, right? Cosecant was defined to be 1 over y, but sine was defined to be y on the unit circle. Secant was defined to be 1 over x, well, cosine is x. Also, another thing that I wanted to mention about identities before we get any further is that a lot of times they might use variables like, notice here they use x as the variable within it, but the letter that's being used in the identity doesn't really matter because the identity is true for any letter, not just x. So like, for example, cosecant of a would be equal to 1 over sine of a. It doesn't matter what letter's in it because it's just an arbitrary constant. Just like kind of how when I wrote x plus x equal 2x, well, yeah, that's true for x, but not just x. It could be any letter. It could be a plus a, right? A plus a is 2a. It's just, a basic logical statement. Again, my camera's in the way. I don't know what I'm doing, being silly because I've recorded too many videos today. But basically, an identity is true regardless of what variable is being used within it. So I'm going to stop being weird and get back to identities. But basically, each one of these, like tangent is y over x, sine over cosine. Cotangent, x over y, cosine over sine. So each one of these is true because of the definitions from chapter 4 based on the unit circle, based on the terminal point, and which is x and which is y, sine or cosine versus sine, respectively. Another thing I wanted to mention about identities is alternative versions of these are also going to be true. So cosecant is equal to 1 over sine, but if I flip both sides of this equation, like if I multiply across by sine and divide by cosecant, it would still be true even if it's, if I took the reciprocal both sides. So sine is also equal to 1 over cosecant, and sometimes there are other identities that are implied based on basic algebra or just common sense as well, which I sometimes might call an alternate version of the identity. But the Pythagorean identities, these ones we proved at the end of 4.4, but these ones were also true because of the unit circle, because x squared plus y squared must be 1 on the unit circle. And each one of these was based on the same premise in which we divided each side by x squared or y squared to convert the form to an alternative form. But each one of these is true because of the unit circle equation, which again is based on the Pythagorean theorem, which is why we call them Pythagorean identities. Now, the even and odd identities, actually, we did not discuss these before because I don't know why. And same with the cofunction identities. We're actually going to circle back to these soon, but actually, let's go ahead and discuss the even and odd identities right now, since I don't think I did this in a video yet. And if I did, I apologize for repeating myself. Um, but basically, these are each true. If you remember back from chapter 2, we discussed what is an even function and what is an odd function, which had nothing to do with even numbers or odd numbers. Remember, even functions had a particular symmetry to them, as did odd functions. And there was a definition which was exactly something like this, which was the mathematical definition of even and odd. But remember that an even function had a particular symmetry to it, that if it did something on one side of the graph, it was going to be symmetric about the y-axis. This is a trait of an even function. And actually notice that if you look at the graph of cosine, cosine started at 1, right, and did something like that. Again, pretend I can draw with my mouse. But since cosine goes both ways, cosine is actually an even function and exhibits even symmetry. And so this is a good thing to remember, is actually all trigonometric functions are either even or odd. They all have a particular type of symmetry. And cosine is indeed even. Whereas sine, if you remember the basic shape of sine started at 1, went up, and went something like that. Well, on the left-hand side, sine did the same thing because it's periodic. But notice that sine actually has the same shape, but also upside down, which is the general definition of what it means to be odd, or the graphical definition. It must be symmetric about both x and y. Or if you kind of remember how I phrased it, it's kind of like you flip it over both about x and y, whereas even functions are flipped over across the y-axis, where odd functions are just flipped across both x and y. And tangent as well is odd because it goes up like that and down like this the other way. But if we look at these identities, that's exactly what they're saying, based on the definition of what it means to be odd. Let me get rid of all that horrible, sloppy writing. But remember that the idea of this is another way I phrased it. An even function, basically it doesn't matter whether you plug in a positive or negative, it's going to be the same answer. Like cosine of pi over 4 is the same as cosine of negative pi over 4. And I believe I have this in a previous slide, so let me see if I can find this. Um, but actually, if I just use the unit circle, it's easy enough to reason why they're even and odd just from the basic circle. Because like, for example, if I'm looking at, say, the cosine of pi over 4, cosine always is x. So cosine of pi over 4 is root 2 over 2. But notice that if I was to go the other way, because this would be positive pi over 4, right, would get me to this point. But if I was to look at what happens if I go the negative direction, the same distance, negative pi over 4, oops, already went too far. Redo that. Negative pi over 4 would put me right down here. And notice that cosine has the same value whether I go the positive direction or the negative direction. And that's exactly why cosine is even, because whether I do cosine of positive pi over 4 or negative pi over 4, I get the same thing. Because really, I'm starting here, right? This is our defined starting point for all angles in standard position. And whether I go up or down, if it's the same distance, positive or negative, I'm going to be in the same x position. So I'm going to get the same answer. Hence, that is kind of the explanation to, well, why cosine minus x is equal to the cosine of x. Because it doesn't matter whether I plug in a positive or a negative, it's equal. And that's what an even function is. It has that symmetry which cosine has, where it's the same on both sides. Whereas an odd function has the exact opposite symmetry, We could see that with the sine as well. Because notice if I do the sine of pi over 4, I get a positive root 2 over 2 because I'm going up, and sine is y. But if I go negative direction pi over 4 instead, I don't get positive root 2 over 2, I get negative root 2 over 2 because it's obviously down instead. So when I plug in a negative into sine, I get the same answer but negative as the positive version, right? Because it's equal to the same absolute value, root 2 over 2, but it is also negative. And this was the exact definition of what it means to be odd. Again, excuse my horrible, sloppy writing there. But anyways, the point was to try to explain the symmetry of those functions and why they're even and odd. Hopefully that is clear enough. But anyways, the algebraic property is just something to remember. And if we think about it a little bit more clearly, basically, and negative within a cosine you can just cancel. It does not matter whether you plug in a positive or negative. So I sometimes call it can eat the negative. Like with x squared, it doesn't matter whether you plug in a positive or negative. It's going to be positive. Same with cosine. It does matter. I mean, it's not necessarily going to be a positive, but the sign will be the same regardless. Whereas with sine, the sign, not sign, not sine, when you use the sine function, the sign will be opposite whether you plug in a positive or negative. Same with the tangent, and that's the idea of even and odd. And the last identities within our fundamental identities are called the cofunction identities. And if you remember, I talked a little bit about how sine and cosine, tangent and cotangent, secant and cosecant, I called them cofunctions because it had to do with the complementary angles within the triangle. We haven't actually proved these yet, but it's actually a lot easier to prove these later. So we'll save these ones for later and talk about those then. But anyways, there are a lot of identities, and this is just scratching the surface of all of the identities that we can do. And one of the key things we're going to work on in the next video is how do we prove a trigonometric identity, and then how do we establish more identities? Where do they come from? What are the logical origins of a lot of the other identities that we're going to study from that cheat sheet? And actually in the slides there's a few other memes. Some of them are pretty funny, but you feel free to look at those and try to figure out the sense of those cartoons from the slides if you want to as well. So anyways, that's enough for this one. In the next one, we will try to prove some new identities. We'll talk about how do you verify, how do you prove them, what goes into that, and we'll practice proving identities. This is a section which is typically hated, but we'll try to focus on the logic of how do we begin, where do we start, and really it just takes practice.